Welcome back to Python tutorial 3. What we have presented is what is the very basic concept behind this discrete Fourier transform, which will be implemented in terms of fast Fourier transform algorithm in Python. And we have seen how to create the X grid. So, there are two steps in the Fourier transforming a function. First, we have to create the K grid, and with the help of FFT FREQ functionality of SciPy FFT pack, and then we have to convert the function with the help of FFT. So, what we have seen here is that the cost function. So, this is your X grid and this is your K grid. On this K grid we are representing it, and we had cos 20 x, this was the function, and once we have Fourier transform it, this is we have defined as y, and once we have Fourier transform it, we are taking absolute value of this yk, plotting the absolute value of yk, because yk is Fourier transform function. Once we Fourier transform it, it is always going to be complex function, and to visualize a complex function, it is convenient to use the absolute value of that complex function, so that we can get an idea what is going on. What we see that we have, once we have converted this cos function, we know that cos omega naught t, when in the time domain we are very much familiar with it, this is the frequency, and frequency is related to the Fourier domain. So, similarly on the x axis, this is the spatial, related to spatial frequency 20, and that 20 is now showing up here, this k naught value. This is actually cos k naught x, and the spatial frequency is defined by this k naught. So, this k naught value is not now showing up. So, we have single frequency 20, but it is showing up in the negative regime also. This negative and positive part is just the consequence of the Fourier transform. It has nothing to do with the practical reality. So, in the practical purpose, we can only note down this positive part of the frequency, and we can take a look at it. The frequency components we are getting only k naught. That should be because cos function is oscillating over the space, cos function are oscillating with the spatial frequency 20, and that is showing up after the Fourier transform. We have only one frequency component, which is 20 on the X grid. So, this is the meaning of the Fourier transform of this function. We will move on and we will check what is going on with the Gaussian function, and we know that Fourier transform of a Gaussian is another Gaussian. So, if I have a Gaussian function in the x domain, then in the k domain I will get another Gaussian function. Okay. But then question is, at what point the Gaussian function will be centered, that depends on okay. So, this is not a simple Gaussian function, it is actually a traveling Gaussian function. So, it has it is a Gaussian pulse, let us say. So, it does not look like this x e to the power minus x square cos 20x, this is the fast moving component. So, this is more like a Gaussian wave packet. So, we should make it a Gaussian wave packet. So, this is the fast component, this is the slow component, which is considered to be an envelope function. So, how does it look like in the x domain? It should have an envelope function, but it is an oscillatory part. So, this is the x domain function look like this, and we need to find out what is the k domain function look like. So, we will move to the laptop now, and in the laptop we will in the program we will make some changes. We keep the x grid to be the same, we do not make changes here. Depending on the convenience, one can change it, but for the time being we will not change it. We will define, when we will define the this Gaussian wave packet on the x grid, we have to multiply it by exponential function, and this exponential function is going to be x square, that is the function. Now, exponential function is not again available with built-in library in Python. So, we have to import it again from the SciPy, and then the k grid formation remains to be the same, it does not have any change. Then the Fourier transform of the functions remains to be the same, and plotting part is remains to be the same. But before we plot that, we will try to plot the function itself first to find out what kind of functions we are considering here. So, plot x versus y, and the limit we have to select. I will check whether this limit will work or not. So, let us run the program. If we run the program, we see that there is a pulse localized. It is not a pulse, it is a wave packet which is localized, but the limit which we are selecting -30 to +30, it is not convenient to look at the inspect that wave packet very clearly. So, we will set the limit to be -5 to +5, -5 to +5. We rerun the program, and we see that it is centered at 0 position and x position, and it is like an wave packet. The wave packet has been at the position. So, at this time, if the wave packet looks like this, what are the frequency components is carrying? That is exactly the information we will get from the Fourier transform. So, this entire function will be Fourier transform now, and if we do the Fourier transform, we will now plot the Fourier transform function, so that we can get an idea of what we are having here. So, k, then absolute values of yk, and limit will change again, because this limit will help us to see everything. What we see is that if we run the program, we see that again there are negative and positive part of the spectrum. We go back to the slide now. What we see here is that this is the x domain, which is representing an wave packet. This is the Gaussian envelope, this is the Gaussian envelope, and the fast varying component is cos 20x. So, this is the, let us say, wave function I have, and this wave function, if we convert it to the k domain. So, this is the k domain. On the k domain, we see that there is always negative and positive part, because the nature of the Fourier transform makes that. But for practical purpose, we can just take the positive part of the Fourier transform spectrum. What we see is that the center, it is centered at 20, and that should be, because we know that from the wave packet discussion of the wave packet is that if I have an wave packet Gaussian wave packet represented by e to the minus x square cos omega naught t, k naught x, it means that this the average component, the spatial frequency component is going to be k naught. So, the frequency components is distributed around this k naught. So, I have this k naught, and then around this k naught all these frequency components, the spatial frequency components are available. So, that is the way we have understood the Gaussian wave packet before, and that is representing here. So, one thing is quite clear from this demonstration, that Gaussian Fourier transform of a Gaussian is another Gaussian, and it is centered at k naught, which is the average frequency component, the spatial frequency component for the wave packet. So, with this we have come to the end of this Python tutorial. What we have learned from this tutorial is that there are two simple functionalities already given in scipy.fft-pack submodule. One functionality will help us get the construct the K grid. Another functionality will help us Fourier transform the discretized wave function from space domain to the Fourier domain. In the FFT FREQ, I need an input. The input is the window length, which is the number of elements in the present in the X grid, and delta X is the spacing in the X grid. And when you are doing Fourier transform of the function, the discretized function, this function name needs to be given. So, with this we will conclude this tutorial. We will meet again in the next module and tutorial.